Ah, hello and welcome to Tensile Ground Coffee. A few minutes on ground engineering to enjoy while having your coffee. So I was thinking about piling rigs and cranes. They are tall structures and of course by their very nature are rather unstable. So it's very important that they have a strong platform from which to work, a working platform. So on ground that is relatively weak, that means you need to construct a platform over that weak ground to provide sufficient support to cranes and piling rigs. So that's normally composed of a good quality, well-graded granular material such as a crushed rock or crushed concrete. So you place that layer on the top on which the piling rigs and cranes can operate. But how thick does that layer need to be? That's what you need to design. That needs to be sufficiently thick so that the bearing capacity of the overall platform and the subgrade are sufficiently high for the piling rigs and cranes that will use that platform. Now, the design methods that exist, some of them are quite difficult to use, some of them are an oversimplification, and some of them are overly conservative. So generally there's some dissatisfaction within the industry about these design methods. So there is a new design method that we have developed that we hope will address some of those concerns. So that's what I wanted to talk to you about in this episode. So over to the flip chart, Brian, and I will explain this new design method. So let's look at the problem of a working platform. So we have a layer, a granular layer that forms the platform constructed out of a granular material. And down here is the subgrade. So a load from a piling rig or a crane, so a concentrated load is applied at the surface that has a width B, and that extends into the flip chart to some length L. What we want to determine then is what is the bearing capacity or ultimate pressure we can apply to that platform QU with a factor of safety applied to have a sufficient bearing capacity for that plant. And we need to set the thickness of that platform H sufficiently large to have adequate bearing capacity. So we need a bearing capacity design method. So at bearing capacity failure, you will have usually punching shear through the platform and then some bearing capacity mechanism that way, or it may go the other way in the subgrade. Now it's a complex interaction between the behavior of the two different materials. That's why some design methods can become rather complicated. But if we express the bearing capacity in this way as a ratio QU over the bearing capacity of the subgrade, if we call that QS, so if there was no platform at all, what would be the surface bearing capacity of that subgrade? So for a clay, in short-term conditions, that would simply be 2 plus pi times the shear strength SU. For an infinitely long strip, or for a square or circular one, we would need the shape factor SC. Now, by back analyzing a lot of physical tests done on this problem, we found that you can express the bearing capacity quite simply in terms of this ratio QU over QS is equal to 1 plus T times that ratio H over B. So a rather simple linear equation in the case of an infinitely long strip. If it's a square load, then you would just need the square term at the top there. So a very simple expression. Of course, you need to know what this T value is. Hence the name of the method, the T value method. It depends on this T value, which tells you how efficiently this load is transferred through this granular material to the subgrade beneath. And it depends on the strengths of the two layers. So by back analyzing a lot of physical testing and numerical analysis, we derive again quite a simple relationship for T. We need to find this value T. If we plot it against the strength of the subgrade, SU, but normalize it so it's dimensionless, so everything is dimensionless, all the units cancel out in all these expressions, which is another big advantage of the method. If we have this expression P prime 0, that is the effective stress on the top of the subgrade due to the self-weight of the platform. And because it's in terms of effective stress, it even takes account of cases where we have groundwater and saturation within the platform. So if we plot T against that and do a parametric study in numerical analysis, we get a series of lines like that, where those lines are the friction angles of the granular material. So that one maybe 45 degrees, that one 40 degrees, that one 35 degrees, and so on. So you see all in one chart, you can see how the bearing capacity of a granular layer in a working platform over a subgrade depends on the relationship between the shear strength of the subgrade and the shear strength of the granular layer. So you could use this as a chart, so you have your SU value and simply read off your value of T and put it into that equation. Or you can use the equations of these lines and just program it into a spreadsheet very easily. Now remember, this is 1 for a strip and 2 for a square. What about in between? You just do a linear interpolation between the two. So it's a very simple and easy to use design method, all in one chart and a very simple equation, and with input parameters that are familiar and can be determined. Simply the shear strength of the subgrade for a clay subgrade and the shear strength of the granular layer. We have also developed a version for sand subgrades, so this instead of SU would need to be the friction angle of the subgrade. And most importantly, it's all being validated by physical testing. So it's been derived by extensive numerical analysis, parametric studies, but validated by centrifuge model testing and by full-scale physical testing. This method also allows us to introduce the benefit of mechanical stabilization with GeoGrid products. So we will be able to put another design line on here after doing the same numerical analysis and full-scale validation. So there you go, an easy to use but rigorously validated design method for working platforms that allows us also to introduce the benefit of mechanical stabilization. So if you have a look at the blog, there are some links to published papers on this if you want to read more about the design method, and there'll also be a link to a web app where you can perform design calculations using this new method. Okay, that's all for this episode of Tensile Ground Coffee. Thanks for watching and see you next time.